The New Quantum Era,
a podcast
by Sebastian
and Kevin Roney.
Welcome back. Hey, after a brief hiatus, I returned to the podcast. Hey, Sebastian. Hey, today we've got a really interesting interview with Professor Yufei Ding, who's an associate professor at UC San Diego. And she's got a kind of a cool background. It's sort of at the intersection between theoretical physics and computer science. So I think this is going to be a good one, Sebastian.
I agree, Kevin, and welcome back. Good to have you back.
Thanks, man.
I met Yufei at a panel at IEEE Quantum Week in Bellevue last September, which is a terrific event overall. The whole week was great. The panel was Academic Quantum Devices and Their Vertical Stacks, Status Quo and Future Roadmap. A little verbose, but it was super fascinating. It was a combination of people working on hardware control stacks that are open source, and the software control stack sort of above that, the controls as well as compilation optimization, and then these sort of system architectures. It was a really, really fascinating conversation. And I was really struck exactly by what you said, where Yufei is sort of coming at this through an intersection of sort of computer science, computer architecture, and the quantum computing side of things. So I thought that was really fascinating, and I'm really looking forward to the conversation.
So awesome. Let's dive in.
Welcome back. So we're joined today by Professor Yufei Ding from the University of California, San Diego. And Yufei, thank you very much for joining us. If you could briefly introduce yourself, that would be great.
Welcome, Yufei.
Thank you. Really, thanks for the great opportunity. Hello, everyone. I'm Yufei Ding. I'm associate professor at the Computer Science and Engineering Department of UCSD. And my research field is mainly two directions. And one is the machine learning system. The other one is quantum computing systems. And you may wonder why I study these two research areas. And I want to give you some kind of introduction to my research background. So I get my bachelor and master degree in physics, and then I switched to computer science and doing my PhD there. And after graduation, I get my faculty job. And at that time, I was thinking, okay, what kind of research direction I should pursue. And one of the direction is continuum of my PhD study, which is a machine learning system. And it's a hot topic. I think it's giving a lot of impact. And another direction I'm thinking of is usually because faculty, I think one or two, maybe two research direction is try to keep your breath and also still keep your depth. So the other research direction I was thinking about that time is about quantum computing, and I think quantum computing is rising at that time. And I also think my background is pretty unique to to explore that direction. So that's why I studied that direction. I think I joined at a very good time.
Did you have a physics background in addition to the computer science studies?
Yes. Bachelor and master degree in physics.
Got it. Okay.
So interesting. And often, Yufei, what we ask our guests on the podcast is, was there any particular moment or influence that powerfully influenced you in the past to, take the choice to embrace, quantum computing as a focused area of study?
So I still remember like when I first study like physics in my college. One of the most interesting and really inspiring course is a quantum mechanics course. And I still remember at that time, like the teachers tell all different kind of phenomena because like how Einstein and a lot of like physics experts like at that time were arguing about like why this could happen and what are the fundamental challenges, what are the fundamental theories. You can feel like sometimes like we always think like if that happens to me, if I was born at that time, can I like really create this kind of theory?
Yes.
So
Yes. Right.
sometimes you feel like, okay, because people sometimes feel some kind of research, they feel like just because like you are not born at that time, if you are born at that time, maybe you can also create it. But some kind of series, you wonder whether you, even like you were like born at that period of time and you have that opportunity, will you really like join this kind of field? Because it's so challenging, it's so transformative, and you always wonder like, because like how can we make this kind of transformative change to be incremental? What kind of research background you need to have to see this kind of new research as incremental research? Because in my field, my feeling is everything after you have good enough background or like understanding of the field, everything can be incremental from some perspective. But if you are missing some technologies or missing some of the knowledge, it will make you like to feel like it's so all of a sudden it's too like the gap is too huge for you to go in. But yeah.
So you're drawn to the really deep unknown questions then, is what you're saying.
Yes.
That's great.
Really interesting. And so, be more specific, please. I mean, which big frontiers have drawn you in? That you think are the most in need of calling out for researchers like you to make a contribution towards?
Okay, so like for my current research is about quantum computing system. I think system is super important, and the reason is if you look at the quantum hardware, you will only have like a few qubits. It's hard to say like what kind of system you want to build. And computer science, if you look at it, like especially system research compared to physics, physics is try to really understand how the nature is working, but computer science is to harness this kind of nature to make it useful. Okay, to make it practical. And we need to build really complex system to leverage everything, to make them like work uniquely and also like smoothly. So there are a lot of design points there, especially when the scale getting larger. So I think that's the beauty of the system research. And I feel like my research is very important is because like it's also like depends on the involvement or the advancement of the hardware development.
Yeah, really interesting. I mean, these pragmatic concerns about system architecture, I mean, we really are at the frontier. I mean, we've only seen a couple of podcast interviews here that really touched on this with depth, but it feels to us like the pace of that research is increasing, right? It's a very creative time in that domain of research. Very interesting.
Thank you.
Yeah, I mean, that was, Yufei, when I participated in that workshop at IEEE Quantum Week, where you presented your work on system architecture, quantum system architecture. That's really when I started thinking, oh, we're going to have her on the podcast for sure, because I thought it was so fascinating. If you look at any particular effort to build qubits, they may be thinking about scaling up a single node. They may be thinking about scaling it to multi-node, but they're only thinking within their own modalities, superconducting qubits or trapped ion qubits or whatever. You're really thinking across modalities, and you're thinking about what role in a system architecture a particular type of qubit may be able to play. Is that right?
Yes, exactly. So I want to highlight a little bit of this kind of function, like decoupling in classical computing. So if, for example, like we already have memory and processing, like the CPU and GPU, and we have the memory system. And the reason we want to decouple them is we only want to focus on some of the functionality at each component. For example, when you have memory, like you can focus on the storage, like the memory size, and usually we do not directly do computation on the memory.
Right.
Because, yes, you can do that, but you really do some simple computations. But that major functionality for memory is loading, storing, and then like because of, and then the processing unit is focusing on different kind of arithmetic control processing. And this kind of function decoupling really create a lot of research opportunities and try to make the system better. Okay. And it's similar to like how we work as a human being. So if you think about one person, if you need to learn all different kind of stuff, it's super hard. So that's why we have different kind of rules. I think similar things can happen in quantum computing and make our system scaling better.
Interesting. And that's interesting too, because in that way you're taking what may be a weakness in a particular modality of qubit in one dimension and focusing instead on the strengths in another dimension. As you said, it may be ideal for storage and not so great for computation because it's not as fast or whatever. Is that kind of the sort of the driver behind the thinking? Yeah.
Yes, exactly. And sometimes it's also like depends on what kind of applications we want to do.
Right.
And that some kind of applications may, for example, like we can have different kind of data encodings. We can use like qubits, qubits, and continuous variables of different ways of encoding. And for different problems, we may, or like even for one problem, different parts of it may require different kind of encoding. And that also requires like different kind of functionalities in your hardware. On our hardware.
Interesting. And I think another big dimension of your research is around algorithms and systems for the interconnection of two remotely separated quantum computing systems and how they could perhaps interact with speed, efficiency, and low error rate. Could you fill in our audience a little bit more in detail how those systems that you proposed work?
Okay. Yes, definitely. So if you think about it, the quantum hardware is trying to scale it up. But when it's scaling up, there's a lot of like fabrication challenges. So if you put too many qubits on one chip, then like there could some like the fidelity of each qubits, like the gate errors could increase. So like one way they are thinking of is using, for example, chiplet to interconnect small chips, and then using distributed quantum computing to connect like larger like chiplets. So this can kind of like create this kind of hierarchical like structure of quantum hardware. Okay. And in that case, you may wonder, like, it's very similar to like what we have in classical computing from single node, like a single core to multi-core to distributed classical computing. So
Right.
very similar to that from that perspective. But then the problem is if you have an application, okay, and like you have to distribute your application like and execute it locally on each of them. And sometimes you need to communication among different kind of chips. And the communication can become the performance bottleneck. Okay. And then like the system is trying to minimize this kind of communication bottleneck. Okay. And so usually one of the strategy is very similar to the classical computing is try to minimize the number of remote communications you need to do or remote gates you need to do in quantum computing. And this is done by like some graph cutting, graph cutting methodologies or techniques. But we are looking a little bit ahead because for quantum computing, sometimes like through one of the communications, you may do multiple gates, and
Right.
that is based on the strength of quantum computing.
Right.
Okay. And that is
I
kind
was
of
about to ask, how does entanglement and superposition actually affect the standard sort of classical perspective on that distributed challenge? Yeah.
Exactly. So it's kind of like a quantum fan out. Okay. Try to do that effectively. Okay.
Interesting.
So usually quantum computing, we know that we cannot clone, and so we cannot easily do the fan out, but they have their own way of doing this kind of cat mode, like cat qubits. And in this kind of cat entanglement states, try to do this kind of quantum fan out and do the optimizations. Okay.
Really interesting. Yeah.
That's great. And when you work on these sort of concepts of system architecture, are you combining, obviously you're using simulators for quantum circuits at this point because you need sort of more perfect qubits, which don't exist yet. But are you also combining like simulators of quantum communication as well? So that, because obviously part of the strategy of distribution requires flying qubits in addition to computational and storage qubits, right? Is that how you sort of try to work on these things?
That's a very, very good question. So currently, like our simulator is still like simple, but we are trying to push it forward using different kind of ways. So what I can tell you is usually like we look through the physics papers, try to understand, okay, what is a remote like the fidelity of the remote gate and try to get information, and then like we want to like really simulate how that remote gate is different from the local gate, and use that information to do our optimizations.
Interesting.
But our simulator is is extensible. So we can also study like if you can improve your fidelity like of the remote gates, and after you like physically improve that link, what is kind of the performance improvement from the system level. So that's why I'm also thinking like the system research is kind of guiding could
Right.
potentially guiding this kind of hardware research before
Right.
we can even like push it forward, try to spend a lot of money to push some of the component into a better shape, because usually we can have different kind of choices. You can improve the links, you can improve the probability of the success, and you can improve all different kind of factors there, like which factor is the most important.
Right.
Oh, I see. So the simulation agenda that gives you perhaps numerous angles of research that allow you to figure out which of the various physical manifestations have to be perhaps pushed the hardest to get to a real life system. Yeah.
Yes.
I see. Yeah.
That's cool. So does that, in your mind, do you think that there is, before we get to those perfect qubits, the fully, fault tolerant quantum computer, do you think there may be interim steps or error mitigated or otherwise fault resistant, but not fully fault tolerant, that might actually yield a useful result in this kind of distributed architecture?
Yes, definitely. I think that is a way around. So like, so I think there are two like research directions we can think of, and one is practically like before we can have the quantum error for tolerant quantum computing with really like large scale quantum error correction code being applied, we can think about quantum like this kind of error mitigation and maybe partial error correction code and how to apply that. For example, we can only like protect some of the logic qubits, which is frequently used, and less protection on those qubits is less used. But we also need to like ensure that error information from the bad qubits do not propagate to the good qubits when they communicate with each other. So what kind of strategy we can use? And we need to have a lot of system simulations, try to give an option there, and try to give a lot of like good ideas, try to explore that direction. And on the other side, I think it also be very interesting to work with physics to understand, okay, what is the extreme between a software like logic qubits and hardware logic qubits. So for example, the topological like quantum qubits, I think them can be as ideal like hardware like protected qubits. Okay, and like for example, like using our superconducting like qubits today and applying the error correction code on that to a larger scale, this could be extreme of the software protected qubits.
Right.
So one in the middle is the best one to design. I think that could leverage our hardware like properties or innovations, but still like effective. So I think it must be something in the middle. And try to go deeper in that direction, being like try to explore different kind of system strategies, try to understand, working with the hardware people, try to understand which part of the qubits can be tuned and which perspective can be tuned, and giving a full knowledge of that part can help us to meet in the middle. Okay. So that is, I think, another very important perspective.
ambitious agenda, very interesting. I wonder, I mean, I'm tempted to now pivot to a separate and very interesting domain of quantum computing research, and you seem like an ideal party to talk to this one about, because there's of course a broad range of both optimism and pessimism about quantum computing. We're believers. It's so interesting and so powerful, but the specific domain, right, of the intersection between machine learning and quantum computing. Many people, of course, just dismiss it as hype, but there's also so much room for optimism. I mean, numerous commentators, Scott Aronson and others, have, underlined the need for rigorous skepticism about these algorithms. What is your level of faith and optimism, right, about the future of how quantum computing could perhaps transform future machine learning research?
That's a great question. So first, let's think about quantum computing for machine learning, and then we can talk about machine learning for quantum computing.
All right, very well. Yeah.
So quantum computing for machine learning. So why people are super interested about it? Because if you think about it, why NVIDIA today is super a big company, and it's a big drive for machine learning, because machine learning is a killer application. Yeah, and once you have this killer application, it has a lot of usage in different kind of domains. People you claim it's a hardware accelerator. It's only useful for some of the applications. As long as that application is very useful, then it becomes super, super important. Okay.
Right.
Yes. So that's why people have the dream, have the passion to push quantum computing for machine learning. And there's something that drives people to think in that way. One of the reasons is nowadays the quantum computing is still noisy, but machine learning has a lot of tolerance for noise. So that's why people feel maybe we can do that, because usually we think everything is a black box, and suddenly it just works. So potentially maybe it could work in some way, as long as we can find the right way to encoding it. So that's why I feel Siritis is more perspective in that direction, but they are pushing in the right way, because sometimes we need to understand what kind of model we need to use and what kind of data encoding we can have here, what potentially of the speed up we can have there. But sometimes even the theory Siritis cannot prove it could work, and suddenly it could work. We can still have the hope there. I feel we are pushing it in both directions, empirically and theoretically. Okay, because it's super important, and if we can achieve the great performance for machine learning, then quantum computing will have a huge market.
Right.
It will have huge potential. Yeah, so that's why people are really push it forwards. Okay, I'm also a little bit conservative, but if I have time, if I have a student, after I study the QEC, I will definitely put him or her on that research direction. If they are also inspired to explore that direction, because once that can be confirmed, I think that will be a huge contribution. Super impact, huge impact. Okay, and that is one direction. And the other direction is machine learning for quantum computing. I think that one is very natural, and because a lot of this kind of system optimization, error correction, error mitigation, the system designs, compilers, architecture designs, everything can be regarded as optimization problem, and machine learning can definitely be helped there. Okay.
Doubtless. I mean, there's so many powerful research results already obtained down this path.
Yes.
There should be no question. And the skeptics there perhaps should quiet.
Yes.
Yeah. That's a really good point. So, I mean, that's a great sort of illustration of why this kind of system approach is important, because you're describing two different technologies really and how they can interact in a systematic way. Throughout this conversation, I just keep on thinking about the way that classical systems have been architected. Really starting from the man who gives his name to the architecture, the von Neumann's efforts at the Institute for Advanced Studies, and there, I think a lot of what the work that came out of there was in response to the fact that they were using war surplus components that were very low quality. They were having to deal with noisy circuits that were prone to failure. And also limited sort of understanding of even the problem space they were going after, right? Beyond just the sort of immediate computations for physics experiments. So do you sort of see a parallel there between, I mean, are you trying to create the Yufei Ding architecture for quantum systems?
That is very ambitious. But yeah, definitely I'm trying to follow a lot of so one of the things I have in mind is usually the philosophy we have in classical computing should still apply here, because that is really we have thinking about for many, many years. But the detailed methodology and approaches could differ. So for example, in classical computing, when we think about the architecture, usually we have two parts. And one is the ESA, the instruction architecture set, which is the interface between the software and the hardware. And then we have the microarchitecture, which is kind of as the implementation of this kind of ESA. Okay, we have different ways. And if you look at the ESA, usually we have like the way we do data encoding. And currently, like we are mostly think about qubits, but in classical computing it's mostly bits, but we also have different kind of precisions. So for example, you have float, you have double, you have like integers, you have different ways. And in quantum computing we have similar, like continuous variable, we have qubits, we have qubits, and then we have a set of instructions. Like in classical computing, we can have the arithmetic operations, we have the control flow operations, and we can have the like memory operations. And if you look at quantum computing today, we are not really having a lot of memory operations because we only have one layers of computation.
Yeah.
So memory is also the compute unit. But later on, you will have more like modularity, like computers, then we may have that component. And mostly like at the beginning of the quantum computing is the design of this kind of arithmetic operations, like the 1 qubit and 2 qubit gates. Okay. And that is from the universal, like what kind of gates are good enough for the universal computation. But nowadays that is extended. So like not only the universal, but in terms of the performance, what is a good like instruction set we want to have there. And then the other one is the control flow operations. Like in classical computing, you can have if else, you can have while. And in quantum computing previously, like when we first have is the earlier version of the IBM and Google machines, they do not have the mid circuit measurement, so they do not really having that kind of control component. But if you think about that, it's kind of, you look at the instruction at the beginning, you will guess you may want to have something like that. And that also gives you the capability of doing error correction code, error mitigation, more fancy.
Feed forward, and all of the all the associated.
Yes.
Yeah, so, and ancilla qubits memory store as well. Yes, I mean many important differences. Yes. Yeah.
Yes, exactly. So if we like, my key point is, if you look at the classical computing, examine each of these components and try to think why they are created and how they are created. What are the research problems? You usually have the same strategy, same problems in quantum computing. And sometimes the problem is more complicated. For example, I want to go back to the memory operations. In classical computing, we have the memory. We have to load from the memory to the processors to do the computation. We do not directly have that in quantum computing, but we have something similar. That is because usually the instruction you can get here can only, for example, 2 qubit gates can only be applied to neighboring data qubits. So then, like if you are applying a gates onto far away data qubits, then you have to do the routing. So this kind of routing can be regarded as one of these kind of memory loading operations. Okay. And so similarly, if you think about the, like in classical computing, we have a big jump from creating this kind of scalar computing to vector machines. Okay. And the vector machine, one of the key idea is a lot of qubits, a lot of bits, they may want to do the same computation. Instead of like directly fetching a one instruction and do one computation, we can fetch one instruction and do a lot of computation. Same computation.
Pipelining.
Yeah, similar. Yeah, a lot of ideas. Can we have that in quantum computing? Because the control is not overhead. Okay, so again, like my key point is, if you examine the whole strategies, if you have a good understanding of the architectures, you'll find that a lot of philosophy will drive you further. Okay.
Yeah. No, it's so powerful. It very much builds on recent results out of MIT and Harvard. It's sort of like the vector parallelization of multiple qubit operations, and those same memory store issues. But they haven't explored the connection of multiple remote systems. So this is rich, deep material. Really, really interesting.
Yes.
So I guess the last question I have for you, Yufei, this is terrific. Your work is really grounded in what's actually being built in the labs, in the experimental labs, right? You're taking a theoretical approach, but you're grounding it in what can be built and what potentially can be realized. Do you get, I guess, a good collaboration with the experimentalists, or do you think there needs to be a better mechanism for the co-design between the theory and the experiment, in the industry as a whole?
Yes, definitely. I think like co-design, try to like let computer scientists and physics working together will be like a big plus. Yeah, it's definitely something we need to do. And one of the reasons is because we are at the beginning, like the interface is not clear. Actually, the interface should be created together with the physicists and the computer scientists. Yeah, and so that's why I'm always exploring like this kind of collaboration opportunity with physics, try to understand their demands and try to understand what kind of hardware they can build, what kind of components or parameters they can tune, what kind of things they can do, and then like try to build our system upon it, and try to understand. So I think that is also called a digital twin of the hardware. Try to understand which part can be tuned, and then like build a system to really evaluate this kind of digital twin before like we spend a lot of money to tune each of the component. I think this could really shortening like how we really get to our final stage.
I wonder, Yufei, I mean, maybe it's just a wrap-up question here, and please forgive me if I'm being too direct, but I'd like to, if you could, try to speculate in a concrete way. I mean, given all this really interesting and vibrant research going on, I mean, at what point within our near future do you think a real multi-tier quantum computing system could we see bring actually to market? I mean, is this a 5-year, a 10-year, a 50-year agenda before we see a real practical system?
I think maybe 10 years is a good timeline to see some practical things. But I think in 5 years, we can really see a lot of near-term milestones. So for example, we're already seeing like how QEC can scale up from the Google experiments and from the YOLS experiments, we first time can see a logic qubits to break even. And I can tell you like a lot of physicists, they feel like the advancement has been much faster than what they expected.
Right.
Actually.
Yeah.
Very true. That's fantastic. This has really been very, very interesting, Yufei. Thank you so much for joining us and sharing your work with us.
So grateful for your time. Thank you. Yes. Yeah.
Well, that was a really fascinating conversation. I really enjoyed it. I hope you did too, Kevin.
Super cool.
Yeah, I mean, I think what Yufei is doing is really interesting in the context of sort of the self-consciousness of trying to reconstruct some critical stages of the development of classical computing. We mentioned Institute for Advanced Studies at Princeton and von Neumann, where he sort of did the groundwork for what now is considered von Neumann architecture, which is, absolutely ubiquitous in classical computing.
Yeah.
Right. And she's sort of taking the learnings from that and trying to find how it applies to the current context of quantum computing and the sort of, the near future of quantum computing, which I thought was really fascinating.
I mean, so cool. I mean, you get the sense that really these days right now, we're living through an era where like just fundamental principles of the future, right, for quantum computing are getting explored and defined, week by week. Really fascinating view on the frontier. I thought it was really compelling also to hear her overall research agenda, an entire simulation framework for these more in-depth and more well-defined system architectures to allow practitioners and experimenters to explore what are viable outcomes. I mean, the rise of classical computing and parallel architectures, there was long before the advent of real physical systems, the simulation agenda was profound, right, in how to map out the best ideas and dispose of the ones that were just fantasy.
Right. I mean, she's bringing that to bear to the current landscape of differing modalities of qubits, super early stage quantum communications technologies, and as you say, creating a framework, an extensible framework where you can sort of model out, like, if we use trapped ion in this way and we use superconducting in this way and we use neutral atoms in this other way, can we combine the strengths of those different modalities into something that is a quantum system architecture, which I think is super fascinating.
So fun. It was also, I think, fascinating to ask the difficult questions about the skeptic's point of view around the possible hype that people feel exists in the intersection of quantum computing and machine learning algorithms. I mean, obviously, there's no question ML has a immense and long, powerful influence already, right, on quantum computing. But the other direction is there some sort of possibility that quantum computing algorithms could be pertinent to future machine learning advances. I like her point of view is that, yes, I mean, skeptics do have a reason to be, doubters. However, should there be a finding in that domain, it could be totally profound, totally transformative.
Right. Because of the breadth of the impact of ML across various verticals, various use cases, if there was some kind of generically applicable quantum advantage to some portion of machine learning, that could potentially have impact across some giant swath of that sort of solution space.
So,
very interesting.
Really good times. Yeah.
Okay, that's it for this episode of The New Quantum Era, a podcast by Sebastian Hassinger and Kevin Roney. Our cool theme music was composed and played by Omar Costa Hamido. Production work is done by our wonderful team over at Podfi. If you are at all like us and enjoy this rich, deep, and interesting topic, please subscribe to our podcast on whichever platform you may stream from. And even consider, if you like what you've heard today, reviewing us on iTunes and or mentioning us on your preferred social media platforms. We're just trying to get the word out on this fascinating topic and would really appreciate your help spreading the word and building community. Thank you so much for your time.